Imagine this. For hundreds of years, the school books we all grew up with have fed us a very neat, very simple story. It goes kind of like this. The ancient Greeks invented logic and geometry, and then, during the European Renaissance, brilliant minds like Newton and Leibniz came along and essentially created modern science and calculus. Nice and tidy, right? But in this explainer, we're going to uncover a massive historical blind spot. We are looking at a grand narrative that actually hides a much bigger, much more fascinating truth about where our numbers and our understanding of the universe truly come from.
So who actually invented modern mathematics? We've been taught this clean baton pass of knowledge straight from Greece to European scholars, but history is rarely that clean, and it certainly doesn't travel in a straight line. Throughout this explainer, we're going to rely purely on historical evidence to challenge that traditional narrative. We're going to see that the math we use today didn't just magically appear in the West. It has roots that are way older, much deeper, and practically brilliant.
Chapter 1. The Great Math Myth.
According to the extensively documented research of Professor C.K. Raju detailed in his works like The Funny History of Arithmetic, a far more powerful system called Ganit existed way before the European Renaissance. Just think about the sheer gap between these two worlds for a second. For centuries, Europe was stuck using what we can basically call Gitti Ganit, or pebble math. They were relying on Roman numerals. I mean, think about trying to multiply CLX by VII on paper. It's a total nightmare. So they had to rely on abacuses and literal pebbles. Fun fact, the word calculus actually comes from the Latin word for small stones. It was incredibly slow and prone to mistakes. Even into the 1800s, prominent European mathematicians really struggled with negative numbers because, well, you couldn't physically take away more pebbles than you actually had. On the flip side, you have the sheer elegance of the Indian Ganit system. They had the decimal system, the concept of zero, and lightning-fast algorithms. They were doing complex, high-level equations while Europe was literally counting stones. So how did this knowledge actually travel? Let's trace this first great transmission of Indian math. Back in the 8th century, Indian texts, including the brilliant works of Brahmagupta, made their way to the famous House of Wisdom in Baghdad. Fast forward to 825 CE, and the Persian scholar Al-Khwarizmi, whose name actually gives us the modern word algorithm, wrote specifically on Hindu numerals and the Indian decimal system was zero. By the 10th century, this knowledge had spread to Arab Spain. But here's the crazy part. When this math finally entered Europe in the 12th century, people didn't trust it. Local laws literally forced merchants to write their contracts in both Roman numerals and the new system just because people simply could not wrap their heads around the concept of zero. It honestly took European scholars hundreds of years to fully trust and adopt the Indian way of calculation.
Chapter 2. Why Ganit was superior.
Why exactly was Ganit so much faster and more advanced? Well, it essentially boils down to one single crucial concept, pratyaksha. That translates to empirical observation. The Indian practice of Ganit relied entirely on direct, real-world evidence and facts. Western mathematics, which leaned heavily on its Greek inheritance, was oriented around rigid, axiomatic proofs. It was almost religious in its dedication to these assumed logical rules, treating mathematical proofs as sacred, even when they completely disconnected from messy, real-world reality. Ganit, though, was firmly rooted in pratyaksha. It accepted facts and empirical proofs, which is exactly how modern working science operates today.
Because of this deeply empirical philosophy, Ganit was never just some abstract, theoretical exercise. If a calculation didn't perfectly match the sky above or the ground below, they just fixed the math. It was actively used to build incredibly complex fire altars, predict solar and lunar eclipses with stunning accuracy, measure massive agricultural lands, and even plan highly advanced ocean voyages. Because it was relentlessly tied to the real, physical world, Indian mathematics managed to stay centuries ahead of Europe.
Chapter 3. The Founders of Indian Mathematics. When we journey chronologically back in time to meet the foundational figures who were laying down the laws of the mathematical universe, the gaps between Indian discoveries and their eventual European adoption are frankly staggering. Take right-angled triangles. Bodhayana mapped them out around 800 BCE. That's centuries before Pythagoras was even born. Sine tables? Aryabhata developed the first proper one in 499 CE, while the Greeks were still struggling with far less practical chord tables. And the area of a cyclic quadrilateral? Brahmagupta had that exact formula nailed down in 628 CE. Europe adopted it much, much later, yet we still call it Brahmagupta's formula today.
Listen to this from the Silba Sutras, written by Baudhayana around 800 BCE. He wrote, "The diagonal of a rectangle gives the same area as the length and width added together." He used practical rope geometry. By the way, Silba literally means cord or rope, to prove what the West now confidently calls the Pythagorean theorem. And they proved it not just by scratching on parchment, but by actually drawing, cutting, and rearranging physical shapes on the ground. They even used ready-made number triples, like 3, 4, 5, to guarantee perfect right angles for massive construction projects.
Then you have the absolute breathtaking genius of Aryabhata and Brahmagupta. Aryabhata didn't just give the world its first proper sine table with 24 distinct values. He calculated the value of pi as 3.1416 and accurately figured out that the Earth actually rotates. Following him, Brahmagupta came along and laid down clear, irrefutable mathematical rules for how zero and negative numbers actually function. He formulated equations for four-sided shapes and was instrumental in linking algebra directly with geometry. These clear, methodical, step-by-step approaches completely revolutionized early astronomy and algebra, and they are the very tools we still rely on today.
Chapter 4: The Stolen Kerala Calculus.
We're now arriving at what is perhaps the most shocking historical shift in this entire explainer. 250. Just keep that number in your head for a second. According to the research, Madhava and the brilliant scholars of the Kerala school developed infinite series for pi, sine, and cosine a full 250 years before Isaac Newton and Gottfried Leibniz. That is 2.5 centuries. They were writing out detailed proofs and doing what we immediately recognize today as calculus long before the European scientific revolution even got off the ground.
So let's unpack how this turned into a massive, quiet transfer of knowledge. Between the 14th and 16th centuries, Kerala scholars were busy writing incredibly detailed calculus proofs in texts like the Yuktivasa. Right around the same time, in the 16th century, European empires were expanding aggressively, and they were desperate. They badly needed accurate navigational math to figure out longitude at sea. Enter the Jesuit missionaries. They arrived in Cochin, Kerala, learned the local languages, and deeply studied these precise mathematical manuscripts. According to the sources, this knowledge was packed up, sent back to Europe, and entirely rebranded. Because, think about it, during the time of the Inquisition, you couldn't exactly go around praising non-Christian sources, right? So the true origins simply quietly disappeared.
Professor C.K. Raju's research puts this dynamic pretty bluntly. He notes, Europeans stole the calculus for trigonometric values needed for navigation, and the followers of Aryabhata in Kerala had derived precise trigonometric values by using infinite series. The research points out the highly suspicious, perfect timing of Europe's sudden discovery of incredibly accurate trigonometric tables by figures like Christoph Clavius. It happened right after European missionaries got their hands on the texts from Kerala. It's a fascinating, complex case of knowledge transfer that completely flips our historical timeline on its head.
Chapter 5: Why this history actually matters.
Now you might be wondering, okay, but why should I care about this ancient history today? Well, because reclaiming this exact narrative is absolutely crucial for how we view education and science right now. It shines a light on a huge core issue in modern education. The dominant Western style of mathematics relies heavily on rigid, formal proofs that can feel totally disconnected from reality. It makes math highly intimidating and abstract for so many students. But the Indian Ganit approach, it's step by step, it uses real empirical examples, and it just feels natural. And because it's so practical, it actually aligns perfectly with how modern supercomputers operate today, because computers calculate using finite numbers, not the impossible, infinite ideals of Western mathematical philosophy.
Professor Raju sums it up perfectly. Ganita makes math easy and enables students of science to solve harder practical problems. The real takeaway here is that honoring the true story of Ganit isn't just about settling old historical scores. It is about building a better, fairer, and a far more effective way to teach our kids and to understand reality today. It's about bringing math back down to earth, to the physical world where it actually works best.
So that leaves us with one final massive question. Are we ready to embrace a fairer, more practical way of understanding the universe? The universe absolutely runs on mathematics, but for centuries we've been fed a very narrow myth about exactly where that math came from. Unlearning that myth doesn't just honor the brilliant empirical minds of ancient India, it actively gives us the practical tools we need to build a clearer, more capable future. Thank you so much for joining me on this explainer. Keep questioning the narrative and always keep learning.